Hi guys, I welcome you to my YouTube channel, Learning Physics with IBM, and today I would like to take you to part 11 of solved past paper questions. Do not forget we are dealing with solved past paper questions from, this is AS Physics. It's AS Physics multiple choice questions, Physics 9702. This is Cambridge. This is kinematics and dynamics, and basically this is going to be part 11. So without wasting time, let's go to the document and solve our questions for part 11. So in part 10, I think we stopped around here, and in part 11, so this is going to be part 11 starting from this page, approximately it's page 95. So this is part 11. So a cheetah and an antelope are 100 meters apart. So they're 100 meters apart. The cheetah spots the antelope and runs towards it. So the cheetah is running towards the antelope, and the antelope reacts to the cheetah after 1 second. So after 1 second, so after time of 1 second, the cheetah reacts. The antelope reacts to the cheetah and runs directly away from the cheetah. Both animals take 2 seconds to reach their top speeds. They take 2 seconds to reach their top speeds. Of course, when they reach the top speed, the acceleration will be 0, so the speeds remain constant. The graph shows how the speeds of the two animals vary with time. So these are the graphs. Okay, so remember, the cheetah was 100 meters. The antelope was 100 meters away from the cheetah. So let's say this is the position of the cheetah, and this is the antelope 100 meters apart. So they are all going to move in this direction here. They first accelerate and reach a top speed. Okay, so how far apart are the animals? 17 seconds. 17 seconds after the cheetah began running. So 17 seconds, I think this is 17 seconds. So this is 16, that is 17 seconds after the cheetah began running. So first of all, we shall find the distance by the cheetah by finding the area under the graph. So I'll call that distance, I'll use D for the cheetah, DC for the cheetah. It's going to be the area under the graph. This is a trapezium. So this side is 15, from here up to here, that is 15. This side is 17, and the vertical height is going to be this one here, which is, I think this is 29. So I'm using the area of a trapezium, where the area of a trapezium is a half into A plus B times H. So distance moved by the cheetah in 17 seconds is going to be a half times A, which is maybe 17, plus B, which is 15, then times the height, which is 29. That is the area of a trapezium. So with my calculator, I'll check this. 0.5 times 17 plus 15, then times 29, which is 464 meters. So that distance moved by the cheetah is 464 meters. Then the distance moved by the antelope, which is also going to be area of a trapezium, that is for 17 seconds. So distance moved by the antelope is going to be a half times. So for the antelope, this is going to be, I think this is 1, 2, 3. So this is 3. So 17 minus 3, that is 14. So it is 14. So that is a half into 14 plus from 17 to this one, which is, I think this is 1 second. So this is for 17 minus 1, which is 16. Then the height is going to be this distance here, from here up to 0, which is 25. So this is times 25. So this gives us 0.5 times 14 plus 16. which is 15 times 25. So this is 375 meters. So in 17 minutes, 17 seconds, the antelope has covered 375 meters. The cheetah was 464 meters. But remember, they were 100 meters apart. The antelope was 100 meters away from the cheetah. So it means the antelope was already 100 meters ahead before running. So its distance of the antelope is going to be actually 100 plus 37 meters from the cheetah, which is going to be 475 meters. So the question is, how far apart? So if this was 475 meters apart, 475 meters from the starting point of the cheetah, then the distance apart, I'm just going to write difference in the distance apart, is going to be 475 minus 464, which is simply going to be 11 meters. So the distance apart is going to be 11 meters. So the answer here is simply 11. So the answer is B. A boy throws a stone with a horizontal velocity of 10 meters per second from the top of a building. The height of the building is 80 meters. The stone travels along a curved path until it hits the ground as shown. How long does it take the stone to reach the ground? So here we're just going to use equations of motion. Since if we assume air resistance is negligible, the acceleration is constant. If I consider vertical motion and I use S in the vertical equals to U in the vertical times T plus a half times acceleration in the vertical times T. If I consider vertical motion, this part here becomes 0. So S in the vertical is 8 equals to a half times acceleration, which is 9.81 times T squared. This is T squared. So I make T the subject. So it is 8 times 2 divided by 9.81 square root of the answer, that is 1.3. So this is going to be 1.3 seconds. That is the time it reaches the ground. So the answer is going to be C. A football is released above a plane sloping surface and bounces several times. The diagram shows its path between its bounces at X and at Y. Assume that there is no air resistance. That means acceleration due to gravity remains constant. So which graph correctly shows the variation with time t of the horizontal component of velocity vh between x and y? Horizontal component. There is no air resistance. Acceleration in the horizontal is 0. Acceleration in the vertical is constant and is going to be 9. Okay, acceleration in the vertical may not be 9. Let's just say a football is released above a plane sloping surface. Okay, so the acceleration due to gravity is 9.81 meters per second because it is released and it just bounces off. It is not moving along the plane. Okay, so if acceleration in the horizontal is 0, it means velocity in the horizontal remains constant. The velocity in the horizontal remains constant because there is no force in the horizontal. So which graph correctly shows the variation with time t of the horizontal component of velocity vh? So this one remains constant. So graph of velocity vertical component with time should be a horizontal line. So A is wrong, B is wrong. The answer is going to be C. Since air resistance is negligible, the only force acting is the force due to gravity, which is vertically downwards. There is no force in the horizontal, so the horizontal component remains constant. So the answer is going to be C. A rocket of mass 30,000 kilograms sits on a launch pad on the Earth's surface. The rocket motors provide an upward force of 330 kilonewtons on the rocket. What is the initial acceleration of the rocket? So we know that by Newton's second law, resultant force F is equal to mass times acceleration. So the resultant force, because the rocket motors provide an upward force of 330,000 newtons, so this is going to be 330,000 minus the force acting in the opposite direction, which is going to be the weight. So minus 30,000 times g, which is 9.81. So for the rocket upward motion, this is the force upwards and then the weight downwards. So the resultant force is the force upwards minus the weight downwards. So it means the acceleration is going to be equal to the difference. So it's going to be equal to this difference, 330,000 minus 30,000 times 9.81 divided by the mass, which is 30,000. So 330,000 minus 30,000 times 9.81 divided by 30,000. So this is giving me 1.19, which is approximately 1.2. So the answer is going to be C. Two equal masses x and y are moving towards each other. That means for one is okay. The diagram is shown here on a frictionless air track as shown. So there is no resistance. The masses make an elastic collision. For an elastic collision, relative speed of approach should be equal to the relative speed of separation. So let's first find the relative speed of approach. So relative speed of approach is going to be 50 minus negative 30, which is equal to 80 centimeters per second. So if the collision is elastic, the relative speed of separation should also be 80 centimeters per second. Remember, a mass which had a higher speed cannot rebound with a higher speed. It is only the one which had a lower speed that could have a higher speed. But the one which had a higher speed in the collision cannot still have a higher speed, or it cannot have the same speed if the collision was elastic. So which law gives possible velocities for the two masses after the collision? Let's first check the relative speeds of separation. So this one is 20 minus 0, so this is out. This is 10 to the right and 10 to the right. The relative speed of separation there is 0. Here it is 20, here it is 0. 20 to the left, 0 to the left, to the 0, then this is still going to be 20. 50 to the right, so 50 to the right minus 30 to the left, so minus negative 30. So this one has now 30, this is 50, so the answer is going to be 80, so the answer is going to be D. Relative speed of approach should be equal to the relative speed of separation. 50 to the right, that is positive. 30 to the left, that is negative, so it is minus negative. The word relative means you subtract the speeds. Which statement is correct with reference to perfectly elastic collisions? Perfectly elastic collisions between two bodies. Of course, we know for perfectly elastic collisions, total momentum is conserved, but also total kinetic energy must be conserved. So let's see, A says neither total momentum nor kinetic energy need to be conserved. They must be conserved. Total momentum and total energy are conserved, but total kinetic energy may be changed. Total kinetic energy must be conserved. Total kinetic energy and total energy are both conserved. That is very true. But total momentum is conserved only if total momentum must be conserved without any condition, as long as the bodies are in an isolated system. Total momentum, total kinetic energy, and total energy are all conserved. So the answer is D. Total momentum is conserved, total kinetic energy is conserved, and total energy is always conserved. Remember these two, total energy and total momentum and total energy are always conserved whether the collision is elastic or not. But if it is elastic, total kinetic energy is also conserved. So the answer is D. A tennis ball is thrown horizontally in air from the top of a building. In the effect of air resistance is not negligible What happens to the horizontal and vertical components of the ball's velocity? It is thrown horizontally. Since it is thrown horizontally, of course, finally it is going to fall like that. So since it is thrown horizontally, there must be force, there must be air resistance, which acts in the horizontal. So that means this is the force due to air resistance. It means the velocity in the horizontal must decrease because of air resistance. And if it is falling vertically down, of course it was thrown horizontally. So air resistance will reduce the velocity component in the horizontal. So we ignore A and B. The velocity in the horizontal decreases. But then as it is falling, velocity in the vertical is equal to velocity in the vertical is going to be increasing. The velocity in the vertical is going to be increasing because there's an acceleration. So it means, but again, it will increase until it will increase to a constant value because there's air resistance. So it will increase to a constant value where the acceleration decreases to zero. When the acceleration decreases to zero, the velocity in the vertical becomes constant. So that means it reaches a maximum value. So the answer is going to be D. Velocity in the horizontal decreases, velocity in the vertical increases to a terminal velocity, to a terminal value which we call, or to a constant velocity which we call terminal velocity. So the answer is going to be D. Why does it increase to a terminal velocity? Because the acceleration decreases due to air resistance. So if the body is falling in the vertical, air resistance is upwards, the weight is downwards. So the acceleration decreases due to the force due to air resistance. So it means the acceleration may reach a point where it is zero, so the velocity remains now maximum and constant. So the answer is going to be D. An object is thrown with a velocity 5.2 meters per second vertically upwards on the moon. The acceleration due to gravity on the moon is 1.62 meters per second squared. What is the time taken for the ball to return to the starting point? Of course, we assume or we know that the moon has no atmosphere, so there is no air resistance. So this is what is happening. The ball is thrown vertically upwards. It comes back to the same level, so the displacement is zero. If I use S equals to UT plus a half AT squared, zero is the displacement. Initial velocity is 5.2 times the time t. But because it's thrown vertically upwards, acceleration is negative, so minus a half times 1.62 times t squared. So I'll just press my calculator to find t. So 1t has cancelled, so I have 5.2 times 2. Then I divide this by 1.62. Then I find the square root of the answer because t is, no, I don't find the square root because I cancelled out 1t. I cancelled out 1t, so I remain with 0.5 times 1.62t being equal to 5.2. That's why I don't find the square root, so it is simply 5.2 divided by 0.5 times 1.62. So this is 6.4. So t is going to be 6.4 seconds. So the answer is going to be D, 6.4 seconds. The graph shows how the acceleration of an object moving in a straight line varies with time. The object starts from rest. That means initial velocity is zero. So let's check. All graphs start from zero. Okay. Which graph shows the variation with time of the velocity of the object over the same time interval? So we want velocity over time of the object over the same time interval. Remember, acceleration is equal to the gradient of a velocity time graph. So initially the acceleration is increasing. So that means the graph should have an increasing gradient. Initially the acceleration is increasing. So the graph should have an increasing gradient. Then at the peak, the acceleration reaches a maximum value, so the gradient should reach a certain value. Then the acceleration decreases, which means the acceleration increases in the negative direction. The acceleration here, the acceleration decreases, so which means the gradient should decrease. It decreases rapidly, so the gradient should decrease. And then at the bottom here, it decreases to 0, so the final acceleration or the final gradient should be 0. So this means we eliminate this one. Okay, this is also showing the final gradient is 0, but the acceleration increases to a maximum value and then decreases. Yet here we see here the acceleration increases, yes, but here the acceleration is equal to 0 at this time here. Yet the acceleration at this time it should be maximum, so B is out. If we look at D, D is showing that the acceleration increases indefinitely. It is still increasing for the same time interval, so this is wrong. Here the acceleration only increases. Remember, the acceleration is the gradient, yet it increases and decreases. So we look at C. C is also going to be wrong because for the first half of the time, the acceleration increases to a maximum value. So yet here it is showing for half of the time, here the gradient increases, then it becomes 0 for a quarter a time. So here the acceleration is 0 at this point. The acceleration is 0 at this point, yet it's supposed to be 0. It's supposed to be 0 at this point here. So it means this is not going to be correct. Then this means this is the correct answer. For the first part here, the acceleration is increasing. You see the gradient is increasing. Then for this part here, the acceleration is decreasing. And for this part here, the acceleration has gone to 0. So the first part, acceleration increases to a maximum value up to around somewhere here. Then for the second part, the acceleration decreases. So it has reached the maximum value, then it decreases. At the final point of time, the acceleration is 0. Remember, the acceleration is the gradient. And at this point here, the gradient is 0 for a horizontal line, so the acceleration is 0. So the graph should go back to the graph. The correct graph is going to be A. An object of mass 4 kilograms moving with a speed 3 meters per second strikes a stationary object in an inelastic collision. Kinetic energy is not conserved for an inelastic collision. After collision, total kinetic energy is 18 joules. Let's first find the first kinetic energy is a half m v squared, which is a half. M is 4, then v is 3, but this is squared, and this is 18 joules. So after collision, total kinetic energy is 18 joules. That would be wrong because it would mean kinetic energy is conserved. So since the collision is inelastic, E2 cannot be equal to 18. In fact, E2 is most likely going to be less than 18 joules. After collision, total kinetic energy is less than 18 joules, so the answer is going to be B. Before collision, total kinetic energy is 12, it is 18. Before collision, total kinetic energy is less than 12, it is 18, so the answer is B. The graph shows how the momentum of a motorcycle changes with time. What is the resultant force? So we know that from Newton's second law, the resultant force F is equal to the rate of change of momentum. Force is the rate of change of momentum. So this is going to be 500 minus 0 divided by 10 minus 0, which gives us 50 newtons. So the resultant force is 50 newtons. A radio-controlled toy car travels along a straight line for a time of 15 seconds. The variation with the time t of the velocity v of the car is shown below. What is the average velocity of the toy car for the journey shown by the graph? average velocity of the toy car for the journey shown by the graph. Okay, so first of all, average velocity is going to be displacement over time. Let's first find the displacement. Total displacement will be the distance here plus the distance here, but they're in opposite directions. So one is positive, one is negative. Distance is the area under the graph, so this is going to be 3 times 10 in one direction minus, this is going to be 6, 15 minus 10, this is 5. So minus 5 times 6. So 30 minus 30, that is 0. So the displacement is 0. So the average velocity is going to be the total displacement divided by time, which is going to be 0 over whatever value of time. So v is going to be 0. So the answer is going to be B, because the displacement is 0, the velocity is going to be 0. This is not standing for speed, it is displacement. Let me just write this because I know students, displacement over time. Two train carriages, each of mass 5,000 kilograms, roll toward one another on a level track. One is traveling at 2 meters per second and the other at 1 meter per second as shown. They collide and join together. So that means they move as a common mass after collision. What is the kinetic energy lost during the collision? Kinetic energy lost, okay. So the loss in kinetic energy is going to be equal to, for the first one, remember kinetic energy is a half mv squared. So the loss, I'll find total kinetic energy before, which is going to be a half times, the first one has mass of 5,000 times its speed, which is 2 squared, plus a half for the second one. Its mass is 5,000 times its speed, 1 squared. That's total kinetic energy before collision minus total kinetic energy after collision. So since they stick together, they move with the same mass, so this will be a half. Total mass is 5,000 plus 5,000, which is 10,000, times the common velocity. After collision, they stick together and move with the common velocity. Oh, I have to find that common velocity. By conservation of momentum, total momentum before collision is going to be 5,000 times 2 plus negative, because the other one is in the opposite direction. 5,000 times 1. So this is total momentum before collision. Should be equal to total momentum after collision. When I write that horizontal line, it will appear as if I'm dividing. So it should be equal to total momentum after collision, which is 10,000 times the common velocity, which I'm going to call v. So 5 times 2 is 10,000 minus 5,000, that is 5,000. So it means v is going to be 5,000 divided by 10,000. So v is 0.5 meters per second. So I'll say times 0.5 squared. So I'm just going to check my calculator. 0.5 for a half times 5,000 times 2 squared plus, of course, a half of 5,000 is 2,500. So this is 12,500 minus, so 0.5 times 10,000 times 0.5 squared. So this is 12. So this is minus 12. How is this possible? 0.5 times 10,000 times 0.5 squared It is 12,000. No, it is 1250, not 12,500. So this is 1250. So the difference, we subtract 12,500 minus the answer. So this is 11,250. 11,250. 11,250. So the answer is going to be C. 11,250 joules. That is the difference. Okay. A resultant force causes a body to accelerate. What is equal to the resultant force? Of course, the resultant force is the rate of change of momentum. So the change in momentum of a body per inch time, that is the resultant force. A ship of mass 8.4 times 10 power 7 kilograms is approaching a harbor with a speed of 16.4 meters per second. By using reverse thrust, that is force in the opposite direction, it can maintain a constant total stopping force of 920,000 newtons stopping force. How long will it take to stop? So let's first find the deceleration, which will be negative. So the acceleration by Newton in second law of force is ma. So the acceleration is going to be F over m, which will be negative 920 because it is a reverse thrust, so it is a stopping force. 20,000 divided by the mass, which is 8.4 times 10 power 7. Yeah, I think most of these are reduced. Let me see. 920,000 divided by 8.4 exponent 7. So that is 23 over 2100. So minus 23 divided by 2100 meters per second squared. That is the acceleration. So we want to find how long it will take, that is time. So using V equals to U plus AT. Of course, when it stops, final velocity will be 0, but it's starting with a velocity of 16.4 minus 23 over 2100, then times T. So I'll take this on the other side, so it means to have 16.4. I'll multiply this by 2100. I'm making it the subject. Then I divide this by 23. And I'm getting T as 1497.4. So T is equal to 1497.4 seconds. So A is wrong, B is wrong. We check the minutes. Divide this by 1497.4. Divide this by 60 to check if to change it into minutes. Divide by 60. That is 25 minutes. So T is equal to 25 minutes. So the answer is going to be C. A tract of mass 1000 kilograms is connected by a tow bar to a trailer of mass 1000 kilograms. The total resistance to motion has a constant value of 4000. So total resistance has a constant value of 4000. 1/4 of this resistance acts on the trailer. A quarter acts on the trailer. Okay. When the tractor and the trailer are moving along a horizontal ground at a constant speed of 6 meters per second, what is the force exerted on the tractor by the tow bar? What is the force exerted on the tractor by the tow bar? So let me just try to sketch this here. Let this be the tractor, and let this be the trailer, and the other one is the tractor. So they're on a surface like that. So this is the tractor, and this is the trailer. They said 1/4 of this resistance acts on the trailer. So the resistance here, remember the tractor, which one? A tractor of mass, this is connected by a tow bar to a trailer of mass. That total resistance to the motion has a constant value of that 1/4 of this resistance acts on the trailer. So, of course, the tractor is the one which is moving the trailer. So the resistance here, I'll change the color. The resistance here on the trailer is 1/4 of 400, 4,000, which is 1,000 newtons. Okay. Since they are moving at a constant speed, the acceleration is equal to 0, so the resultant force is 0. So there is tension here. There is tension there. So when the tractor and the trailer are moving along a horizontal ground at a constant speed of 6 meters per second, what is the force exerted on the tractor by the tow bar? What is the force? So the answer here is just going to be, so since the resistive force here on the trailer is 1,000 and the acceleration is 0, yet the only forces acting is tension and the resistive force. So the resultant force F, which is mass times acceleration, is going to be equal to, since it is moving forward, it's going to be T minus the resistive force, which is 1,000. But at constant velocity, I'm looking at the trailer alone. At a constant velocity, acceleration is 0, so 0 is equal to T minus 1,000. So the question wanted us to find the force exerted on the tractor by the tow bar. So that is the tension. So the tension is going to be 1,000 newtons. So the answer here is going to be B. The graph shows the variation with the time of the speed of a raindrop falling vertically through air. It is falling through air. Remember this, for speed time graph, the gradient is the acceleration. So at this point here, the acceleration is 0. At that point, the velocity is constant. The resultant force F is 0. That means if the body is falling, if a raindrop is falling in air, its weight must be equal to the drag force in the opposite direction plus the upthrust if the upthrust is there. So let's check the options. Which statement is correct? The acceleration decreases to produce a steady speed. Of course, that is very true. The gradient here is showing that the acceleration is decreasing. At this point here, the acceleration is 0. So the acceleration is decreasing to produce a terminal velocity. So the answer is automatically A without wasting any time. The answer is A. An experiment is performed to measure the acceleration of free fall g. A body falls between two fixed points. The four measurements shown below are taken. Which measurement is not required for the calculation of g? Okay, so we can think of a simple equation. S equals to ut plus a half at squared. We want to find g, so we may need to find s, distance falling through, that is fine. We may need the initial velocity u, that is fine. In this equation, there is no mass, so the answer is C. The mass of the body is not required because if the acceleration is constant, all objects, so for whatever mass are accelerated at the same rate. So the last one, the time taken is fine. We need the time, but we don't need the mass, so the answer is C. In a cathode ray tube, an electron is accelerated uniformly in a straight line from a speed of 4 times 10 power 3 to 2 times 10 power 7 meters per second over a distance of 10 millimeters. Since it is accelerated uniformly, equations of motion can work, such as v squared equals to u squared plus 2as. Our final velocity is 2 by, I want to find the acceleration, so acceleration is going to be v squared minus u squared over 2s. So this is going to be 2 times 10 power 7 minus 4 times 10 power 3 divided by, this is going to be 2 times s, which is 10 times 10 power minus 3 to change it to meters. So this is going to be 2 exponent 7 minus 4 exponent 3 divided by 2 times 10 exponent minus 3. So this is giving me 9.998, or I can say 1.0 times 10 power, is it 1? Sorry, these are squared. Sorry about that. I have to check this again. 2 exponent 7 squared minus 4 exponent 3 squared. Yes. Divide by 2 times 10 exponent minus 3. So that is 1.999. That is 2.0 times 10 power 6. 2.0 times 10 power 16 meters per second squared. So the answer is going to be D. The graph shows how the speed v of a sprinter changes with time t during a race, a 100-meter race. What is the best estimate of the maximum acceleration? So remember, for a velocity against time graph, acceleration is equal to the gradient. So if we want a maximum acceleration, we look for a part of the graph which is the steepest. And I think this is the steepest part of this graph. This is the steepest part of the graph. So the acceleration here is going to be maximum because this is the steepest part of the graph. So the acceleration is going to be 8 minus, I think this is a 1. This might be 1 approximately, divided by 4 minus, I think this is 2. So that is 7 divided by 3, divided by 2, which is, that would be 3.5. So what is the best estimate? So this is out, this is out, this is so big, so the answer is C, the best estimate. So maybe this may not have been exactly 1, it could be around 1 point something, but is approximately 3.5, and the closest value there is 3 meters per second. So the best estimate is 3 meters per second. A tennis ball is dropped onto a table and bounces back up. The table exerts a force F on the ball. Which graph best shows the variation with time t of the force F while the ball is in contact with the table? Of course, when the ball just hits the table, when the ball is just hitting the table, initial value of F is 0. So that means D is out. The table does not exert any force just at that instant when the ball just makes contact, or at the instant it also doesn't make any force when it doesn't exert any force when they separate, at the instant when they just separate. So it means C, so it means D is going to be out because this is showing that there is a constant force throughout. At the moment when it is just in contact, and even when they separate, it is showing that there is a constant force, which is not true. At the moment when it is just in contact, the force increases from 0 to a maximum value. Then at the point of separation, the force decreases from a maximum value to 0. That is exactly what happens. So at the point of this one is showing the force increases throughout, so this is also out. After an instant, of course, we know that force is equal to the rate of change of momentum. And now momentum is mass times velocity. So as the ball gets in contact, V goes to 0, momentum changes. So the ball exerts a force on the table, and by Newton's third law, the table exerts an equal and opposite force. So at the instant when the ball just makes contact, the speed has not yet changed. So momentum has not yet changed, so the force is initially going to be 0. So the force will initially be 0. That's why D is wrong and B is also wrong, because B and D are showing that the force is initially not 0. So the initial amount of force should be 0, because before the velocity changes, before the momentum changes, it means the resultant force is 0, because force is the rate of change of momentum. So at the instant that when the ball just makes contact, the speed has not yet changed. So it means momentum has not yet changed. So if momentum has not yet changed, and when there is no change in momentum, the force is going to be 0. And that's what makes B and D out. So initial force should be 0 at that instant when they just make contact. So B and D are out. Then the change in velocity and the change in momentum are going and the change in velocity and change in momentum become maximum. F will be maximum at this instant when the change in momentum and the change in velocity are maximum. Of course, change in momentum is directly proportional to change in velocity. Change in momentum is directly proportional to change in velocity. So at the point of when contact has occurred and the velocity tends to 0, then the change in momentum, the change in velocity is from maximum to 0. The change in momentum is maximum because it's directly proportional to the change in velocity. So it means the force at this point must be maximum. The force reaches maximum. But then the speed of the ball must increase in the opposite direction. The speed of the ball increases in the opposite direction while still in contact, but now force of the ball is going to be away from the table, and that means in the opposite direction than before. In opposite direction than before. So the resultant force from the table gradually now decreases as the ball tends to move away from the table. So that means A is wrong. Of course, B and D were already wrong, so the answer is going to be C. The force must gradually increase and then decrease between these 2 points. So only C could be correct. So when the ball is getting into contact, the force is initially 0 just before contact, but then it becomes maximum. And then when the ball tends to move away from the table, the force gradually changes to 0. So force from 0 to F, a maximum value, then from maximum value back to 0, which makes the answer to be C. A stationary ball explodes into two components of masses m and 2m. The components gain kinetic energies x and y respectively. What is the value of the ratio x over y? Okay, so let's use conservation of momentum first. It is initially stationary. A stationary body explodes into two components of masses m and 2m. So total momentum before explosion is 0. Total momentum after explosion, for let's say to the right positive, the left negative. So it will be 2m times its velocity. I'll call it v for y. Then plus negative, because it is in the opposite direction, m times its velocity. I'm going to call it vx for mass x. So if we simplify this equation, notice that Vx is going to be twice Vy. Vx is twice Vy. That means kinetic energy for x is going to be a half times its mass, which is m, times its velocity, which is twice V. Let this be just twice V. So times 2V squared. Let Vy be just V. So I'm saying let velocity of y be simply v. So Vx is twice V. Then kinetic energy of of y is going to be a half times the mass, which is 2m, times its velocity, which is v, but squared. Okay, so let's find the ratio. What is the ratio? Value of x over y. So kinetic energy of x over kinetic energy of y. So of course, if you simplify this kinetic energy of x, it will be 4v squared times m over 2, which is 2m v squared. And this one, when you simplify this, it is going to be m v squared. So the ratio is going to be equal to 2m v squared divided by m v squared, which is equal to 2 divided by 1. So the answer is C. A shot put champion accelerates a 7.0 kilogram metal ball in a straight line. The ball moves from rest, initial velocity 0, to a speed of 12 meters per second in a distance of 1.2 meters. Assuming the acceleration is constant, we shall use equations of motion. So what is the average resultant force? Average resultant force on the metal ball. So let's first find the acceleration. From v squared equals to u squared plus 2as. From v squared equals to u squared plus 2as. The ball moves from rest. So we have that v squared is 12 squared equals to 0 squared plus 2 times the acceleration times 1.2 meters. So what is A? A is going to be equal to 12 squared divided by 2 times 1.2. So 12 squared divided by 2 times 1.2, that is 60. So acceleration is 60 meters per second squared. So we want to find the force. So force is equal to, resultant force is MA, which is going to be 7 times 60. And this is going to be, I think that is 42, 7 times 60. So this is 420 newtons. So the answer is going to be C. A ball drops onto a horizontal surface and bounces elastically, meaning kinetic energy is conserved. What happens to the kinetic energy of the ball during the very short time that it is in contact with the surface? The very short time that is in contact with the surface. Of course, the very short time when it is in contact, the velocity goes to 0. In that time, the velocity tends to 0. Before it grows, of course, that is before it grows back to rapidly to another value or before it grows back to the original value in the opposite direction. So the kinetic energy, most of the kinetic energy is lost as heat. Remember, it is elastic. The kinetic energy remains constant because it is an elastic collision. The kinetic energy, in that very short time, the velocity rapidly goes to 0 before it changes to another value. So the answer is going to be B. The kinetic energy decreases to 0 and then returns to its original value. So that is because at the point of contact, the velocity rapidly goes to 0 before it grows back to its value in the opposite direction. So the answer is going to be B. The acceleration of a free fall on the moon is 1/6 of that on Earth. On the Earth, it takes time t for a stone to fall from rest a distance of 2 meters. What is the time taken for the stone to fall from rest a distance of 2 meters on the moon? Okay, so they have told us that the acceleration of free fall on the moon, g on the moon, is equal to 1/6, 1/6 of g on the earth, which I'm just going to call small g. So it means g is equal to 6 times g on the moon. Okay. So I am going to come up with two equations using S equals to ut plus half at squared. Since it is falling freely, that means initial velocity is always 0. The distance is the same. So let's start with the moon. On the moon, S is 2 meters, initial velocity is 0 equals to half. G on the moon, I am calling it G subscript m times T times T on the moon, I'll call Tm squared. Then on the earth, S is 2 equals to half. G on earth is 6 times gm. 6 times gm, because g on the earth, this is g on the earth, which is 1 over 6 times g. So g on earth is 6 times g on m, which is going to be 6 times, no, this is not correct mathematics here. Okay, so I'm just going to use g on the earth is 6, g on the moon, so times time on the earth is simply t, but t squared. So gm cancels when I divide the two equations, a half cancels when I divide the two equations, 2 cancels when I divide the two equations, so it means a tm squared is equal to 6t squared. So when I find the square root, it means tm is going to be t. Now remember I divided the two equations. Okay, I divided the two equations. This is not correct. When I divide the two equations, on one side I have 1 over, okay, 1, I think that is correct. When I divide, 1 is okay, so tm squared is equal to 6t squared. So square root tm is going to be t times the square root of 6, so the answer is going to be C. I divided these two equations, so 2 cancels, half cancels, gm cancels, I remain with 1 on one side is equal to tm squared over 6t squared. So tm is going to be equal to t times the square root of 6, which is C. Which graph represents the motion of a car that is traveling along a straight road with a speed that increases uniformly? If the speed increases uniformly, the acceleration is constant. So that is a horizontal graph for acceleration against time. If the speed is increasing uniformly, speed with the time, it will be a straight line like that. A straight line like this one will have a uniform, will give us a constant gradient for acceleration, because acceleration is equal to the gradient of a velocity time graph. This will be a constant gradient, which gives us a horizontal line for acceleration. So the answer is going to be A for acceleration. So this is wrong for acceleration. This one shows constant velocity, which is 0 acceleration. Yet the speed increases uniform. This one is constant velocity. This is 0 velocity. So here V is constant because the gradient is the velocity for a displacement time graph. Here V is equal to 0 because the gradient is 0 for a displacement time graph. What is the principle of conservation of momentum? For an isolated system of interacting bodies, total momentum remains constant. So the answer is going to be, this is C. Total momentum of a system remains constant provided no external forces act on it. If no external forces act on the system, it is said to be isolated. Water is pumped through a hose pipe at a rate of 90 kilograms per minute. It emerges from a hose pipe horizontally with a speed of 20 meters per second. Which force is required for a person holding the pipe to prevent it moving backwards? So that is conservation of momentum, and then force is equal to the rate of change of momentum. So this is going to be mass into change in velocity divided by t. So the mass per unit time is 90 divided by time, which is 60, because it's 1 minute, so that is 60 seconds. The velocity changes from 20 to 0, so that is times 20. So this gives us, I think this is automatically 30 newtons. So the answer is going to be A. Two railway tracks of mass m and 3m move towards each other in opposite directions. In opposite directions. with the speeds 2v and v respectively. These tracks collide and stick together. So they collide and stick together. What is the speed of the tracks after the collision? So I'll use conservation of momentum. Because they are moving towards each other, if momentum of m is positive, m times its velocity, 2v, plus the momentum of 3m should be negative, so it will be minus 3m times its velocity v. That's total momentum before collision. This should be called total momentum after collision. Since they stick together, total mass is going to be 4m, then times the common velocity, which I'll call u. So this is 2mv minus 3mv, which gives us minus mv, and the other one is 4mu. So m cancels. So u is going to be equal to negative v divided by 4. So the answer is automatically going to be A. The velocity, the speed is negative v over 4. In other words, the speed is in the direction of the 3m mass. That's what the negative is showing here. A mass m is situated in a uniform gravitational field. If I had done 3mv minus 2mv, it would be positive, but that doesn't matter. The mass of m is situated in a uniform gravitational field. When the mass moves through a displacement x from P to Q, it loses an amount of potential energy E, which row correctly specifies the magnitude and direction of the acceleration due to gravity in this field. So this is a gravitational field which is moving in the direction. Of course, the mass is moving from P to Q in the direction of the field. Since motion is in the direction of the field, the body accelerates, but it is a uniform field, the acceleration is constant. So motion in direction of speed, not in the direction of speed, motion in the direction of the field. What is wrong with this pen? Okay, so motion in the direction of the field, it is moving from P to Q. That is, it is moving along the field. When the mass moves through a displacement x from P to Q, it loses amount of potential energy. It is losing potential energy. So it is actually, if it is losing potential energy, then it is moving in the direction, of the field, because potential energy is equal to mgh. If h decreases, potential energy decreases, and h only decreases when the mass moves in the direction of the field. So if it is losing potential energy, then it is moving in the direction of the field, so h is decreasing. So which row correctly specifies the magnitude and direction of the acceleration due to gravity in the field? So the direction of the acceleration, since it loses energy, so the direction of the acceleration in the field is to the right, so we ignore B and D. If it is losing energy, it is moving in the direction of the field, so the field is to the right hand side. But then what is that potential energy that it loses? So potential energy is equal to m g h. Which row correctly specifies the magnitude and direction of the acceleration due to gravity in this field? So energy is mgh, where h is the distance x, so energy is going to be mg times x. So the magnitude is going to be E divided by m times x. So the answer here is going to be A. In an experiment to determine the acceleration of free fall g, a ball bearing is held by an electromagnet. When the current to the electromagnet is switched off, a clock starts and the ball bearing falls. After falling a distance h, the ball bearing strikes a switch to stop the clock, which measures the time t of the fall. Which expression can be used to calculate the value of g? So using equations of motion, s equals to ut plus half at squared. It is falling, initial velocity is 0, the height it falls through is h, so h is equal to a half. Acceleration is the acceleration due to gravity, which is g t squared. So it means g is going to be twice h divided by t squared. So g is twice h divided by t squared, which makes the answer to be D. The diagram shows a velocity time graph for mass moving up and down on the end of the spring. It is moving up and down. Which point represents the velocity of the mass when at the lowest point of its motion? Of course, at the lowest point of its motion, velocity is supposed to be 0. At the lowest point of its motion, velocity is supposed to be 0. But remember, this is up, this is down. So here the velocity is maximum, here it is passing equilibrium position. So this is equilibrium position. Velocity is 0 when it is going downwards. Sorry, yes, velocity is maximum at equilibrium position. So it was going upwards. It is going upwards. Let this be equilibrium. So starting with 0 velocity at this point here. So here it is, this is point A. This is the origin. Then here it is moving beyond equilibrium to if it goes beyond equilibrium, so this is going to be point B where velocity becomes 0 at the highest point. Then now when it is falling, it is now moving in opposite direction. So here is going to, it is passing equilibrium again, so this is going to be point C. Velocity is max, here it was maximum in this direction. Now it is maximum in this direction. And then it goes to the lowest point where velocity is again going to be maximum. Velocity is again going to be 0. That is at point D. So which point represents the velocity of the mass when at the lowest point of its motion? So the answer is going to be D. It can't be 0, 0 because at A it is passing equilibrium. At B it is at the highest point up. And at C it is passing equilibrium but in opposite direction. So here is at equilibrium. Here it is at the highest maximum height up. Here it is at equilibrium but in opposite direction. So at D, it is at the lowest point where velocity is again 0. Lastly, a ball is released from rest on a smooth slope xy. It moves down the slope along a smooth horizontal surface yz and rebounds elastically at z. It rebounds inelastically at z. Of course, at this point here, it is a straight line. It's a horizontal line, so the acceleration here is going to be 0 because the speed is going to be constant here. But of course here, it is released from rest, initial velocity is 0. At this point here, it is moving on a horizontal surface, it is smooth, no friction, so it moves at a constant acceleration. So A should be constant here. Here A should be constant because it speeds up uniformly. V increases uniformly since the surface is smooth. Then at A, because the surface is horizontal, the speed remains constant, no speeding up, acceleration will be 0, V will be constant here. Okay, let's see now the graph. Of course, it rebounds inelastically. If it rebounds inelastically, it means V must decrease. V must decrease on rebounding. And of course, since the surface is smooth, V is going to be smaller, but will be constant, decreases, but to a constant value. it's because this part is horizontal, so it is going to be rebounding, but to a constant value. V will decrease, but to a constant value. Okay, so which velocity time graph represents the motion of the ball? So the first part is showing constant acceleration. So this is constant acceleration. This is zero acceleration, then rebounding, again zero acceleration, then constant deceleration. Okay, so let's check. I think the answer is automatically going to be A, as opposed to, because this part here, constant acceleration, zero acceleration on the horizontal part. Okay, so since it momentarily stops, or since momentarily it is momentarily going to be at rest, then since momentarily at rest, then there will be more time to get to rest. So that means the time here, this one here, V, it is showing that V decreases, but it is taking a longer time. V decreases, but then takes a longer time to reach Y. So B is out. So V decreases, but then it is going to take a longer time to reach Y, because since the speed is, since the distance Y to Z is the same, since it rebounds to the smaller speed, it must take more time to reach Y. So that means B is out. Since V decreases for B, since V decreases, so the time should be longer to reach Y. So T should be longer to reach Y from Z. But this one is showing that it reaches Y in a shorter period of time. So that's what keeps B out. And of course, D is out. D is out, because it is showing that it rebounds with the same velocity. Remember, it is inelastic. It is inelastic. So the velocity with which it rebounds is not the same as the velocity is smaller. So V decreases, so it must be smaller. So it means this one is out, because this velocity, the maximum velocity here, is the same as this one, yet it rebounds with a smaller velocity since it is inelastic. That's why it is out. So we had to choose between C and A. We had to choose between C and A. In both cases, acceleration is constant. Acceleration goes to 0. It is taking almost a longer time to reach it is taking a longer time, almost the same time to reach Y, but this one shows it takes a shorter, there's a smaller deceleration here as compared to this one here. So it means because the momentarily comes to rest, then it needs more time to rest. So the answer is going to be A. Okay, so that marks the end of part 11. See you in part 12 at this point here. Part 12 at this point here. I think you learned something from this. You can always leave a comment. I may not be very accurate on everything. You can always leave your comment. I'm always willing to adjust. I'm always willing to correct where possible. But thank you for watching my videos, and bye bye.